So far we have looked at the first and second isomorphism theorems. In this video, let us start with the third isomorphism theorem. Recall that isomorphism theorems are statements about isomorphisms among quotient groups. Okay, the third isomorphism theorem will say a similar statement to the first and second. So let us see what it says. Let G be a group. Okay, let H n be two normal subgroups of okay. In the second isomorphism theorem, we work with two groups, one normal, the other arbitrary. In this case, we take both to be normal. So H and N are both normal subgroup of G. Then we have two statements. So actually I should write let H and let H and N be normal subgroups of G such that N is contained in H and H is contained in G, of course. So I am taking two subgroups, one containing the other. N is contained in H and both are normal. N and H are both normal in G. Then we have two statements. Then G, then H mod N, because N is a subgroup of H, I can consider H mod N. Remember, N is a normal subgroup of G, so it is certainly a normal subgroup of H. I want to say H mod N is a normal subgroup of G mod N. So we will explain this. So H mod N, first of all, I want to think of it as a subgroup of G mod N, and then I want to further say it is a normal subgroup of G mod N. And the second statement, which is actually what we call third isomorphism theorem, is that G mod H is isomorphic to G mod N mod H mod N. Okay, so this might seem ugly here, but the point is H mod N is a normal subgroup of G mod N by the statement 1. So I can consider the quotient group G mod N modulo H mod N, that is same as G mod H. Okay, this is a very useful theorem actually, third isomorphism theorem along with the first isomorphism theorem. They both get used a lot. Here think of this as sort of cancelling. G mod N mod H mod N, it's like almost like you cancel when you write ratios of numbers, right, integers, you can cancel. Something like that you can do here. That is why this is very useful to write it like this. G mod N mod H mod N is isomorphic to G mod H. That cancelling is valid is what third isomorphism theorem says. So first of all, let's tackle one. We want to show that H mod N is a normal subgroup of G mod N. In order to do that, we first want to even think of H mod N as a subgroup of G mod N. Before we even ask whether it's normal subgroup, is it as subgroup of G mod N. Note that we have H is a subgroup of G. So we have an inclusion H in G, right? So this inclusion is simply sending small h to small h. We also have a natural homomorphism G to G mod N, right? So let's put these two things together. We have H to G, which is natural inclusion. So in particular, it is an injective map. It's a 1-1 map. And then we have the natural surjective map from G to G mod N. Remember, when I talked about the quotient groups, I defined this natural map that exists always. A G goes to Gn. This is a group homomorphism. That is this second map, G to G mod n. So consider the composition. This composition. What is the composition? H to G mod n, right? But it is actually going via G. So first you send it to G and then you send it to G mod n. So this is really nothing but small h going to Hn, because under this composition here you see that under the first map you take a small h, it goes to small h under the first map, and the second map takes small h to small hn. So under the composition small h goes to small hn. Okay, what is the kernel of this? Kernel of this map is h in h such that Hn equals n. Remember, n is the identity element of G mod n, the identity coset is the identity element. But as before, this is an h in h. In the second isomorphism theorem also this came up. So it's in h in h, but it's also in n. This of course is h intersection n, but in the new hypothesis, remember, n is also a subgroup of h. So this is just n. So kernel of this map is n. So by the first isomorphism theorem, h mod the kernel, which is n, is isomorphic to the image of this map. I don't care what it is, it's a subgroup of G mod n is all I care about. Is isomorphic to a subgroup of G mod n. And as I have remarked in a previous video, after I did the first isomorphism theorem, if you have a situation like this, the technically precise statement is h mod n is isomorphic to a subgroup of G mod n, but we can think of as a subgroup of, okay, so we think of h mod n as a subgroup of G mod n. We are claiming in the first part of the theorem that h mod n is a normal subgroup of G mod n. I have justified that it is a subgroup of G mod n. Now we have to show that it's a normal subgroup. What is a normal subgroup? So we have h mod n inside G mod n. Normality means what? You take something from the bigger group, something from the smaller group, and consider the element by taking inverse and product. So what is an element of G mod n? It is of the form Gn. What is an element of h mod n? It is an element of this form, because these are left cosets of n in h. So G is in G, h is in h. And what do we consider? We consider this G mod n, Gn times Hn times Gn inverse. Let's understand this element. What is this? This is really an operation of cosets, but we have worked with cosets now in several videos, so this hopefully will be clear to you. It's easy to see that this is Gn, Hn. Remember, in the quotient group G mod n, the inverse of the coset Gn is simply given by G inverse n. This also something we have shown while proving that G mod n is a group when n is a normal subgroup of G. Gn whole inverse is G inverse n. Okay, so now let's write it like this. So we have Gn, Hn, G inverse n. Okay, so we have this. Because of associativity, we can rearrange our brackets. So I'm going to write with, I'm basically going to get rid of the brackets and write it like this. Let's look at this part. N G inverse. In some previous video I commented that if n is normal, so note that if n is normal in G, then Gn equal to Ng for all G in G, right? So this means that Ng inverse would be equal to G inverse n. So Gn H G inverse n n. So I am just switching Ng inverse and writing it as G inverse n. But this is Gn H G inverse n is n. This is a property of left cosets. If you product really of subgroups, n is n. So this is n. But now I can, using the same property that Gn is equal to Ng, pull H and G on this side. So this will be GH n G inverse n, which is same as, so I am interchanging n and h here. Now I will do n G inverse. So GH G inverse n n, which is of course again GH G inverse n. Okay, so though this seems somewhat magical here, and you might be worried about whether all this is valid or not, you have to convince yourself that this is valid, because all I am doing here is multiplying subsets of a group, and multiplying subsets of a group follows the same rules as multiplying elements of group, and we are using here the properties of normal subgroups, and if n is a subgroup, then n equals n, and everything else is correct. So all this is a valid operation. So GH, so okay, let's now take stock. Where are we? Gn Hn G inverse n is equal to GH G inverse. Now I am going to use the normality of H in G. GH G inverse belongs to H, right? Because G is in capital G, H is in capital H, so GH G inverse is in, so G is in H, G is in G, H is in H, so this is in H. So GH G inverse n, so is in H mod n, right? Because this is in H, this is a left coset, this is a left coset of n in H, which is by definition an element of H mod n. So we have now proved that H mod n is a normal subgroup of G mod n. This proves that H mod n is a normal subgroup right. We have started with an arbitrary element of G mod n and an arbitrary element of H mod n, and looked at Gn Hn Gn inverse and concluded that it's in Hn, which is the definition of H mod n being normal in G mod n. So this is 1. 1 is exactly that statement, and it is proved now. So let's prove 2 now, and prove 2 is the statement that G mod H is isomorphic to, we'll show G mod n, G mod H is isomorphic to G mod n mod H mod n. Okay, so how do we show this? So again, whenever you have a statement that you have to prove, which involves proving some quotient groups are isomorphic to each other, think of constructing appropriate group homomorphism and invoke first isomorphism theorem. As you have seen in the proof of the second isomorphism theorem, it is really an application of the first isomorphism theorem, and here also it will be an application of the first isomorphism theorem. the map to consider here is the following. Let me consider this map from G mod n to H mod n. What is this map? I'll take a coset of G mod n, element of G mod n, which is a coset of capital N and capital G. Alright, so I'll take a small g in capital G. So actually, sorry, this is not a map to H mod n, this is a map to G mod H. Okay, so I take a small g in capital G and consider the coset Gn. I'll map it to GH. Okay, so this is the map. Gn goes to GH. Certainly GH is an element of GH, G mod H, right? Because it's a coset of capital H in capital G. So phi must be well defined in order to be a group homomorphism, right? Before that you have to check well definedness. Why do we need to check well definedness here? Because we can have Gn equal to G prime n. This can happen for two different elements of the group G. Even if they are different, Gn could be equal to G prime n. Suppose this happens. We want to check that phi Gn equals phi G prime n. Otherwise it's not well defined, right? You have one element which has two different representations, and using the representation, if you send it to different elements, it's certainly not a well defined map. So we want to check that GH is equal to G prime H. But if Gn is equal to G prime n, remember this means that G inverse times G prime is in n. This is because you can multiply by G inverse, so n will be equal to G inverse G prime n. That means G inverse G prime will be in capital N. This is this kind of thing we have seen before, right? If G inverse G prime is in N, then G inverse G prime is in H, because N is contained in H. By hypothesis, N is contained in H. So we have this. But if G inverse G prime is in H, GH equals G prime H, right? So well definedness is okay. If you have two representations of the same coset, they will also give you the same coset in G mod H. So if Gn equals G prime n, GH equals G prime H. So this is okay. And phi is a group homomorphism. This is easy. This is easy because what is phi of Gn times G prime n? This is phi of G prime n. This is by definition G prime H, and this is equal to GH G prime H, and this is phi of Gn, right? So phi is a group homomorphism. I am checking every detail here, though it's not difficult to check them. What is the image of phi? I claim phi is onto. Why? Phi is a map from G mod n to G mod H. So what is an element of G mod H? An arbitrary element of G mod H is a left coset, right? So it's GH. Then phi of Gn is GH. So you take the same element small g, Gn maps to GH. So phi is onto, right? This is trivial. You take a coset, it's certainly the same element times n maps to it. So it's onto. What is kernel of phi? This is what we have to check now. What is kernel of phi? Okay. So kernel of phi is by definition all elements of G mod n. So all elements of G mod n which are denoted by G capital N. Remember, these are cosets. So all elements of G mod n such that phi of Gn is equal to the identity coset, right? Identity element of G mod H is GH, H. So this is equal to that. But this is Gn in G mod n, Gn in G mod n such that GH equal to H. Remember, phi of Gn is by definition GH. So phi of Gn equal to H means GH equal to H. That means Gn equal is contained in G mod n such that G is in H. Right? So these are cosets of the form Gn in G mod n such that the small g is in capital H. But what is this? If you think for a second about this, these are left cosets of small g, these are left cosets of capital N in capital G, which are also left cosets of capital N in capital H, because this G must be in capital H. So this is just H mod n, right? H mod n, remember, is Hn, H in H. H mod n is the cosets of capital N in capital H. So they are of the form Hn, small h n, small h in capital H. But this is really what we are doing, right? We are taking all G in H and taking G mod n, Gn, sorry. All G in H, so instead of calling it small h, I am calling it small g here. So you are taking small g in capital H and taking Gn. So this is exactly H mod n. Okay, so kernel of phi is H mod n. Now, what is the situation? Phi is a map from G mod n to H, G mod H. It's a group homomorphism onto kernel equal to H mod n. Now what does the first isomorphism theorem say? Again, it's the final point is the consequence of first isomorphism theorem. You have a group homomorphism which is onto and kernel H mod n. So you have G mod n, which is the domain group, modulo the kernel, which is H mod n, I have computed that, is isomorphic to, so remember, G to G prime is a group homomorphism, means G mod kernel is isomorphic to image. So I am applying it to G mod n to G mod H, it's a group homomorphism. So G mod n modulo kernel, which is H mod n, is isomorphic to the image, which is G mod H, because it's onto. And this is exactly what we want to show. G mod n mod H mod n is G mod H. Right? So we have finished the proof. So this is exactly the isomorphism that we have claimed, and we have proved this. So this completes the proof of the third isomorphism theorem. So together this first, second, third isomorphism theorems are very important, and as you have seen in the proofs, it's clear that the crucial observation came from the first isomorphism theorem. Then it is just looking at more and more special cases to get second and third isomorphism theorems, and these are used frequently in many theorems, and in future classes we will see this. So it's important that you carefully work out the proofs and make sure that you understand all the details. So I'll stop here. In the next video, I'll look at some more applications of these quotient groups. Thank you.